Before we get started, just a little bit about myself. I've been a practicing engineer for just over 30 years now. I spent my first 20 years in capital equipment, mainly semiconductors, but also surface mount pick and place. A lot of machine parts, a lot of assemblies, almost all manufactured here in the US. In the last 10 years, I've moved over to consumer products, working for iRobot and Europro and now Dragon, so mostly manufacturing in Asia, mostly injection molded plastic, circuit boards inside, and so on. So it's been kind of a survey. The examples we talk about today will basically all be mechanical examples because everybody understands mechanical parts. But you can apply it to other things, electrical assembly, for example. Great. So this is the textbook that Sean stole all the examples from. And you'll see eventually some of the illustrations look like they were drawn in 1952. They look old even to me. Okay, what's DFMA? Design for manufacture and assembly. I think we all know what manufacture and assemble means. And the whole idea here is you want to make it easy to build and easy to assemble for a couple of reasons. One is it's cheaper. The second thing is it's more reliable. If it's so simple that a baboon could put it together right, the odds are it'll always get put together right. Easy to assemble, it's almost always easy to service. And folks often think of this as something to worry about shortly before they launch into manufacturing. But the reality is I've been through too many rounds of prototyping where the prototypes were so hard to assemble and fell apart so quickly, the software guys couldn't develop the software, the EE guys couldn't debug their circuit boards. And so doing a little bit of this up front, even in the very beginning, can save you tremendous amounts of time in development because it makes it easy to build and easy to service because your first prototypes are probably going to be pretty crummy and they're going to get fixed a lot. What we're going to talk about today in the presentation is going to be a specific means of analysis to determine whether an assembly is efficient to manufacture and efficient to assemble. And it gives you a numerical score you can use to say this is a good design or this is a bad design. But it's important not to get too wrapped up in the numbers and to think about what it means. Most folks put very little time and effort into this, and if you just apply some effort, some brain power, and use some common sense, you'll make an awful lot of progress towards having a good design without even worrying about the fancy analysis. So historical design method, and you see what I mean by the illustrations from 1952, was the engineer designs it and heaves it over the wall and manufacturers got to cope with it. I spent many years over here, and the guys in manufacturing complained about the stuff our teams turned out, well, they were just sissies or something. And later in a I don't know what kind of career move it was, I actually ended up in manufacturing. And downstream from the engineering department, downstream was almost never a good place to be, and found out it really is a problem. And when I started my career 30 years ago, the companies I worked for, the factories were in the basement of the building I was in or across the parking lot. And if you release something stupid to the floor, well, a big burly guy with hair in his knuckles would show up in your office demanding that, genius, you come down to the floor and show us how to put this thing together. But nowadays, you design something, you release it to China, the burly guy with hair in his knuckles can't make it to your office to motivate you. Everything's handled via email with a 13-hour time difference, and you've got language barrier and so on, or you're handling it through local people, and it doesn't work very well. In addition, a lot of engineers these days, since they're not growing up with manufacturing right in the basement, they're not getting that feedback, and they're not getting a chance to learn in the way that I got to learn when I had that guy with hair on his knuckles yelling at me. It means that you guys, as design engineers, have got to put a lot more effort into this up front, and it'll pay big dividends, or it'll at least prevent big disasters. Okay, this is a relatively fancy way of for the author of saying that enough effort put into concept design up front, and here he's talking about ease of manufacture and ease of assembly, will pay big dividends later, where using a proper process, putting more effort into concept design and getting the DFMA right means design goes faster, there's fewer design changes, it's easier to communicate the information, and if you don't follow it, the point he's trying to make is not enough time in concept design, a lot more time put into engineering because you get a lot more parts and it's a harder project to put together. It's harder to communicate the idea, and then you've got a lot of problems to fix later, and this is absolutely true. So a little bit of effort put in up front will pay big dividends, and not just in manufacturability and ease of assembly, but in cost, quality, and the like. Another concept you've probably seen is the engineering department may be 5% of the total cost for a corporation, but he may affect or influence 70% of the product cost in the end because of the decisions that he or she makes. And unfortunately, this is also the point at which you're frequently in the biggest rush. So corners get cut, things that are released without being finished, and so on. So here's where we get into the method of analysis. And there are really just two variables, the number of parts in a product and the ease of assembling those parts. And parts count is extremely important. In my past lives, when I've done a cost reduction exercise and gone through the design of a product and cut the parts, the idea is you cut the number of parts in half, and the average cost per part goes up, say, 30%. So you have a net gain, a net cost reduction, but you end up with fewer, higher quality parts that you're to put together. So instead of 18 pieces of sheet metal that have to be put together with slots and adjusted into place and maybe bent a little bit, you go to 3 or 4 machine parts that are turned out in a CNC mill and are always accurate and bolt together on pins. And the baboon I mentioned earlier could put it together and will always get it right. Part necessity. First thing you have to determine is if a part is necessary. And the first rule they follow is, does it move relative to another part? If it doesn't move relative to another part, you combine it. Does the part have to be a different material? I.e., one part has to withstand high temperature, the other part has to have low coefficient of friction, and you can't get something that does both. Does the part have to be separate for assembly purposes? Imagine you've got a circuit board inside a plastic case, and the case has 2 halves with a circuit board inside. There's no way you can mold that case, all at once in one piece with the circuit board nicely captured inside, or at least it would be extremely difficult. Here's an example. This is a motor that mounts to a kind of a base plate. There's an end plate that goes on the end of the motor, and this whole cover, which is open at this end, although it doesn't show you, slides over it and is fastened from here to here to enclose the motor. So you can see everything's put together with screws and set screws and so on. And this is a design not unlike some that I've seen. And the point they make is the base is sort of the first part they start with, so they're going to assume that that's required. And there are these porous bronze bushings put in here for reasons we know not why, because there's no other part in there. So presumably something is going to poke in through the hole in the end plate and have to pivot in that bushing or slide in that bushing. This motor may actually be a lead screw actuator, for example. But you could make this base out of Delrin, perhaps. So in theory, at least, those bushings are not needed. Okay, the motor, you buy it, you don't build it. It has to be a separate part. You've got no choice. The screws, in theory, you could get away without using them. The motor could be press fit. There could be snap retainers machined or molded into the base. And it should be important to keep in mind as we construct a theoretical minimum parts count, it doesn't mean that you actually can or would want to build something with that small a number of parts. It's frequently not economically practical, might not be easy to assemble, but it gives you a measurement point, a guidepost for understanding whether your design is efficient or not. Okay, sensors, it's a separate part that you buy. You can't integrate it, so it's necessary. More screws, in theory, not necessary. The sensor could be press fit in. Standoffs could be part of the base, not necessary. End plate, and it's separate because you have to capture the motor against that part. Okay, end screws, again, not necessary. Maybe it could be a press fit, maybe it could be snap features. Plastic bushing, maybe the end plate could be made of the proper plastic or otherwise similar features. And the cover could perhaps be made in one with this end plate. And like I said, the other end is open, so it's actually, the assembly would be like a cup, and that's why you can do that. Okay, cover screws, likewise, theoretically not necessary. The author does then is, in a table of numbers, lists all the parts, how many there are, how many are actually theoretically necessary, and there's only 4. The actual assembly time and the assembly cost, assuming $30 an hour. And then they have something they call an assembly index, and this is just kind of an arbitrary measurement point to compare the performance of your design to the theoretical minimum. And they take the theoretical minimum number of parts times the theoretical minimum amount of time to assemble it, and the author's assuming 3 seconds, and so 3 seconds is what it takes to put a pin in the hole, for example. And that's 12 seconds, and you divide it then by the actual assembly time, which is 160 seconds, this total here, and that gives you 7.5%. It's generally considered that 25% is a decent design. So you would look at that and you say, gee, I've got some room for improvement. I ought to be able to improve this by a factor of 3. And so before we go on, any questions about what we've just done and what this table shows? Okay. This is essentially a ratio of the theoretical minimum amount of assembly time it would take to assemble a perfect design divided by the actual assembly time. They get the actual assembly time here, and presumably this has been measured. It might not be makeable. It's makeable, but there would be other reasons not to be there. You're almost never going to, 25% is pretty good. You're not going to get to 100%, except for some trivial, simple examples, perhaps. So is that clear? Okay. So now the redesign that the author gives as an example is that the cover and the end plate have been combined. The bushing is made in the bushing for getting the wires out is made in one with the cover. And he does retain a set screw for the sensor because he must have decided he can't press fit it, and that's probably true because temperature sensors like this have very thin sheet metal housings. And there's 2 screws to mount the motor because he decided he probably didn't want to press fit it, and that's a good idea. You'd destroy the motor. So that's the best that you can do practically speaking. And if you work through the numbers, now he's at 26%. And so that's pretty important because if you look at that, there's not much room to simplify. That last version was a nightmare of parts, and this thing's pretty sparse, but he only got to 26%. So that's a pretty good design, and that's another reason why you probably will never see 100%. Okay, and he makes the point that when you do design for assembly, this whole thing manifests itself in part manufacturing costs. My experience has always been, and this is in part due to a portion of my career spent as a quality engineering and manager, is it makes huge differences in product quality. Just getting things that always go together reliably and always in the right manner will sharply cut down on defects at the factory. The other thing that happens if you have capital equipment that has to be serviced in the field, as I used to, you cut the parts count in half, you probably cut the number of spares you have to stock. And spares that are stocked are a big capital expense for the company. And when a product line is discontinued, almost always the field spares get scrapped, and it's a huge hit to the bottom line. So let's go through as a group and see what we think the minimum parts count would be for these 4 examples. Okay, this one in the upper left, 2 brackets, screwed on with washers and nuts to a base plate. Anyone want to hazard a guess? Anyone else? Yeah, 1 part. How would you make this part if it was you? Yeah, U-channel. Bend a piece of sheet metal. Okay, how about this one? What do we think the minimum parts count for that is? 2, right. How would you hold the cover on? Yeah, that's a good way. How about this one, C, where you've got a plate covering a hole in that base plate? And I'm assuming that hole is an important feature for some reason. Something locates to it. Yeah. How would you make the part, do you think? Okay. Well, I'm sorry? Oh, Yep. Okay. And how about this one? I believe this is a terminal strip. And these are screws binding posts for connecting wires to. Yeah, I don't think it can be reduced any further. Yeah. The screws have to move relative to the base. Okay, ease of assembly. We're talking about part handling. Obviously, symmetrical part is easier than an asymmetrical part. You don't have to worry about it. You just shove it in. Slightly asymmetric. Does anybody think that's a good idea? No, why? Because Bruno, the guy with the hair in his knuckles, he's going to make it fit no matter which way it lies. So instead, you have this, big flat taken off, and maybe there's a feature right here on the other part, so even Bruno can't put it in the wrong way. Okay. Anti-jamming, have you ever seen some plastic cups or even glass tumblers? They get jammed together and you just can't get them apart. And this is why that's there. And you see this in many other features like waste baskets, for example. There'll be an indentation on the bottom, just enough so you can't jam them together, so the guys in the warehouse don't have to rip them apart. Anti-tangling. With this device, this gap is on the order of this dimension, so these could all get linked together. You pick up one, it would make a chain. You have to spend all this time on linking them. Okay, too small apart. Whoops. Too slippery apart. It's sharp and you stab your worker. That's not good. It's flexible. It's hard to pick up. It gets tangled, apart. And I think this is like a disc maybe that fits into a hole and it jams and cocks if you don't put it in perfectly. In this example, he makes it thicker so it'll slide into place. Also giving an example of where pushing a pin into a blind hole because of captured air pressure can be a problem. I've seen that occasionally. So you're putting relief holes to let the air out, or a hole in the pin, or flatten the pin. Oops. At this point here, you imagine trying to put this spring into a deep bore. You can't see the bottom, so which means lots of times it isn't going to go into the bottom. It's going to get hung up on there, and the whole thing will be assembled. The spring will be cocked and jammed together. So he puts a chamfer, and it just automatically goes all the way to the bottom. Okay, pyramid assembly. In this example, you just stack the parts up 1, 2, 3, 4, right from one side, no problem. Any 3-year-olds who've mastered the color rings on the post will know how to do this. This example, you have somebody where the worker has to line things up while putting the assembly together. And here, because there's a counterbore, the parts are self-aligning. This again falls into the category of a baboon could assemble it. Okay, standardizing common parts. See, in this example, you've got a bolt and a nut. Here you've got a bolt or a screw, rather, just going into a tapped hole. So you might have 4 screws, but 2 nuts on hand. Okay, here's a part that's just about impossible to assemble because the pin doesn't make the hole before you have to let go of it. So you lengthen the pin or make the bore shallow, and it becomes a lot simpler to do, although this is still pretty hard. Okay, costs of fasteners. Here you have a molded in snap. And this one, I think they folded up a tang and pinned it over. Then you have a separate double-ended rivet. And then finally a tap hole with a screw that's screwed into place. Okay, here you have an assembly that when you're halfway done, you got to flip it over and do the other side. Always better to be able to do it all from one side, especially if that's heavy. I used to work on pieces of equipment that would fill this room. You don't have the option of flipping it over and screwing it from underneath. You have to do everything from one side. With process, I'm going to kind of skip through this and not get into too much of the details. The author does make a good point that the designers are a person with a hammer, and everything looks like a nail. And they've all got their own hammers, and so a guy from an injection molded background, he wants to mold everything. Somebody from a machine parts background, they want to machine everything. And a professor I had in mechanical engineering at Cornell back in the late 70s gave an example of how when he was a young man and was working during the Second World War, was part of some civilian office that had to do with procuring military equipment, and he had to evaluate prototypes of different pieces of equipment. And one of the projects he was responsible for was an anti-aircraft gun mount. And they had 3 corporations bidding. They had, I think, General Motors, USMC, which is United Shoe Machinery, and somebody else, maybe General Electric. And these were big hydraulically driven anti-aircraft mounts that were linked to radar systems and all very high tech for the time. And so they had an evaluation of the 3 designs, and he went through them and he said that the unit from GM looked like it had been made in a car plant. Sheet metal stampings and so on. The unit from USMC looked just like automated machinery for making shoes, castings and ground ways and so on. And so these were guys who knew how to do things one way, and that's how they were going to do it. So it's important to keep that in mind because sometimes you're not going to pick the optimal design approach. The author goes into some detail about all the different processes you might know and the point that most engineers are ignorant about an awful lot of them. So nothing we want to go through in detail, just the idea that a lot of times a process you're not familiar with can save your butt. I'm thinking about a time when I was designing semiconductor process chambers, and we had this one oxidation process that took place at 1200 degrees centigrade, and the atmosphere was gaseous hydrofluoric acid to act as a getter to remove metal ions during the oxidation process. And these were quartz bell jars, but they had to have a metal flange to allow for seals and gases to be introduced. And we kept turning these $30,000 flanges into lumps of green slime, and that kind of expense adds up fast. And what saved us in the end was we were able to find a proprietary coating, which was a hard coat with an impregnated Teflon, which is able to withstand the corrosive process, and it turned out to be very inexpensive as well. So it was something I knew nothing about. I had the good luck to have an engineer who had used this once in a past life, and he said, no, this will work. So lots of times a different process will really save you. Different materials he talks about, and mostly he's talking about plastics here. The same rule applies. Okay. This is the slide I really didn't understand, Sean. I have to confess I don't understand this chart at all. It seems to say that cast iron cannot be sand cast, when of course we all know that principally. Oh, so it's for the particular part. Okay, now I understand. Mm-hmm. Right. So you end up with a list of the things that would work. So it's kind of a mind-broadening exercise to force you to look at the different materials and the different processes. And then the no draft requirement, for example, would be one of the reasons why most of the casting operations are not going to work. Right, nowadays. So this would take you through the whole process. Okay, and this is the textbook this was taken from. Okay, this is the end of the slideshow part. I want to talk a little bit about just my practical experience. I've only ever gone through this exercise in training courses and so on. I've never actually done it in course of a project. The reality is you get a couple of good people, around a design on a table, you can beat your way through the solution pretty quickly. And it all revolves around how do we cut the parts count, how do we combine the parts, how do we make sure that the parts are moldable or machinable, that they can be assembled. And mostly you do this working with physical prototypes, working with drawings and so on. So common sense and some effort applied, and you'll get there pretty quick. Now, at this point, it might be good if, I know some folks had some prototypes, at least I saw some floating around. Is there anything anybody wants to bring up for discussion?